So I have. So I remind you that this afternoon at 6 p.m. I guess we have the BMAX lecture. We have invited a guy from Boston, and he's delivering a speech on artificial intelligence, and I don't remember what, but for sure, I mean, this is it's going to be quite interesting. And this is the first announcement, so this is just a reminder. The second reminder, which of course arrived yesterday from Professor Borgonovo, is about our, IBM seminar. We have next Tuesday and the Tuesday after that. So on Tuesday, November the 2nd and November the 9th. Both in the morning, because you have no classes in the morning. I don't know. I mean, I'm going. Last year, I don't remember if they required the students to sign up to the IBM Quantum website. I'm not sure about that. I will check that. But please take a look at your Bocconi email, because if you need to create an account on the IBM, which is something you get for free, on the IBM website for quantum computing, because probably they will be, say, giving you some experiments to do maybe from 1 week to the week after, and just compare the results or something. I will tell you in an email, okay? And that is the second announcement. And the third announcement is that I am Professor Baldassi. No, because I'm not dressed in black. That's the reason why. Otherwise, you wouldn't get the difference. Same size, same weight, but not the same color. That's the key. Okay. Okay. So, what is the purpose of these 5 lectures? I mean, in the first 3 lectures, more or less, I will introduce you back to nonlinear optimization, which is something that we touched a bit last year. Of course, I know that you spent most of the summer reviewing my lecture notes on optimization. Yes, of course, so you are very proficient, but it might be the case that someone came just, say, from other courses this year, so maybe they don't know. And so, I'm reviewing all the things. I'm giving you a bit of, so I published my lecture notes, so the starting page is exactly the same as the definition of norms and inner product that you have on the other notes, the one in, say, in applied math. And apart from that, we will walk through derivatives, and then the differential, and then we will talk about all the operations that are considered in this case. At some point, there are no exercises for these 5 lectures, because you'll have plenty of opportunities to experience with these things, with numbers, with Professor Baldassi, of course. We will show you the code for implementing most of these things. The reason for having this introduction is that you can't tell a computer what to do if you don't know what the computer will be doing, what the computer is going to do. I mean, you have to understand the issue, and this is the reason why we are focusing on this right now. Otherwise, it's just, I mean, copying and pasting the code without understanding anything. Okay, so the purpose of this is to analyze, as I said, nonlinear optimization. Did I start the recording? Yes. So nonlinear optimization so just to give a meaning to the title of these 3 lectures. Nonlinear, because there is a kind of a linear optimization. Essentially, the problems in optimization, I will get back to this later on, but the problems are like, you want to find the extreme value, in most cases could be the minimum, but could also be the maximum of some, say, function f of x, and in general, x is a vector in Rn. And of course, since we want to find the minimum or the maximum, it means that the function, it means that the output, the values must be in an ordered field. Okay, so usually this is R. Now, usually the problem is not just like this. It also adds another requirement, that the variable x is in a set A, which is usually a subset of Rn. So you are, this is the jargon, constraining, this is called a constraint. You are constraining the variables because the variables cannot take any value in Rn, okay? Because otherwise, there will be no linear optimization, because of course, if you have just straight lines, planes, hyperplanes, there is nothing to optimize. I mean, the surfaces are flat, and of course, if you go one or other direction, you get large or small values as you want, okay? So linear optimization means techniques you use, special techniques that you use for solving problems where everything from the function f to the constraints are defined using linear functions, which means, well, functions of degree one in all the variables that are involved in the function. Non-linear optimization means the general case. Now, why this distinction? Because for linear optimization, there are special techniques that use this fact, the fact that the function is linear, to solve some problems. If you go to, if you look packages online that solve, even I guess SciPy has, even in SciPy, you have different opportunities, different methods to solve problems, and you have to tell the computer what is the problem that you're going to, what is the method that you're going to use. And of course, if you know that the constraints of the function are linear, you use a linear method, the simplex algorithm, for example, and other things. And if the function is non-linear, you use other algorithms. The ones that, well, I will give you a brief overview about. So we are concerned with nonlinear optimization, and in most of the say the statements, we will talk about minimization. So we will be interested in a problem like finding the minimum of a function f of x over a predefined domain for the x's. Why the minimum? Well, you probably already know this, because most of the problems in artificial intelligence are written as models. In these models, we want to find the better approximation to something, and to find what better means for the scientist is usually to have what is called the minimum cost. You define the cost typically, but probably you are better than I am at doing this. You define the cost as being the difference between the expected value when you know what the value of the say the output of the model should be, and the value that the model gives you. Okay, so and the idea is that you somehow measure these things, and you want these things to be as small as possible. This is the same approach that is used in statistics when you want to find the line that the regression line with the number of data. Just to give you an idea, because you haven't done any regression. I mean, the idea is that you collect some data about some fact, and then you want to find a straight line which sort of represents the data. What you are doing in this case is, well, this is the data, so this is the real world, and this is the model. And what you are doing in these cases is, well, you take for every, so these are the x's and these are the y's, and you take every value that is the real value, the value that you got from collecting the data, and what the model is predicting with the same x, okay? And of course you get, usually you never get the model right, okay? So you always get these segments, and these segments represents the errors that you are making in using the model instead of using the data. But of course, the advantage of using the model is that you can predict something, okay? So you can say what is, in your opinion, the value for an x that for which there is no data. And the idea in least squares is that you take all these lengths and you add the squares of these lengths, and so you have a sum of say, this is, call it say epsilon, I don't know, n, this is epsilon 1, this is epsilon 2, or whatever. So you get epsilon 1 squared plus epsilon 2 squared plus dots plus epsilon n squared. And of course, these epsilons, also the lengths of these segments, depend on the slope, on the choice that you make for the line. So essentially, they depend from two numbers, m and q, or, well, in statistics, they use a and b. Sorry, they use beta and alpha. Okay? And so you want to find the beta and the alpha such that this is the takes the minimum value. Yes, please. Yes, I'm recording. I'm so you can't, you don't, why? I don't know. I mean, I'm recording. So you guys online, can you hear me and see me? I guess otherwise they would complain about this. Yeah, because probably it's a matter of the projectors here. Would you like the projectors, or wouldn't you like? I mean, it's the same. Okay. Well, this is a double check for what is broadcast. No, because this comes from the projector. I mean, it comes directly from the, doesn't go outside and gets back here. Okay, so that is the idea. So you want to find the minimum, the beta and the alpha, such that this is the takes the minimum. Okay. And of course, every epsilon is a function of beta and alpha. I'm telling you this because, well, this is a very simple example, but what you see is a sum of squares. And the sum of squares, in the best that can happen is that the sum of squares is 0, which is the minimum value, which corresponds to a case that is technically highly unlikely, that is all the points lie on a straight line, which is something you don't expect in the real world. But this is our objective, and this is what you do in most of the things in say machine learning and artificial intelligence. You define a cost, and then you want to minimize the cost. Find the parameters in the model such that the cost is minimum. Well, in statistics, they will probably tell you the reason. The reason is that you want to find, well, essentially, you can't take the values because otherwise a negative error and a positive error will cancel one another, and that would be a bad thing. That is one thing. Informally, I can tell you that if you take the squares, small errors count less in the sum than large errors. But actually, there are good technical mathematical reasons for this. And essentially, the idea is that this is a measure of the error which is consistent with all the things in statistics. Yes, that is the reason for using the square and not, for example, the absolute value, which would will be the length, okay? Because the length is always a positive number. So that is the reason why. Technically, we say this is an unbiased estimator of something. Okay, so as you remember, well, this you remember for sure in high school and last year, for finding the minimum of something, you need to use derivatives. And so we are now introducing derivatives again for multivariable functions, and briefly go through, say, a review of all the things that we have seen last year. Okay. So the starting point is always, in my notes is definition 1.5, is always the directional derivative. So we take a function f defined on a subset of Rn with real values. So this is a function that takes a vector and outputs a number. The most basic case is when n equals 2, and you have a function that takes a point in the plane and associates to that point a number. And in that case, you can see the function because you can graph the function in a three-dimensional space. We assume that A is an open set. We assume that X is in A. And we also assume that Y is a vector in Rn such that the norm of Y is 1. Why these assumptions? And I'm not going, say, all of the theorems are say, use the same assumptions here. Now, first of all, we assume that A is an open set, which means that whatever we are saying is true. Essentially, all the points of A are interior points, which means they have a neighborhood around them. And that neighborhood, in that neighborhood, you can compute something. Essentially, we are not in the, say, at the border of some region in Rn. So we are not considering these, say, special cases. This is true for most of the problems in optimization, because you assume that the range taken by the parameters is something like an open set. Of course, if A is not open, some things might change, but this is not something that we are considering now. Then we take a vector y, and the only condition about y is that the norm is equal to 1. The norm of y is equal to 1. This is just a technical condition about what we are going to define. Essentially, y represents a direction. So we are now considering what is called the directional derivative, f of xy, which is the limit as t approaches 0 of f of x plus ty minus f of x over t. If f prime of xy exists and is finite, we say that the directional derivative of f at x along the direction y is, well, the directional exists and is f prime xy. So what is the directional derivative? We are considering a function. We are considering a fixed point, x, in that function. We are considering another point, but now we see y not as a point, but as a direction, okay? So we are adding y multiplied by t, and t is a number that approaches 0. So the displacement from x, instead of the one-dimensional case, the displacement could be in, say, infinitely many directions. In the two-dimensional case, this is obvious. Of course, it is true also for the multi-dimensional case. And the idea is that you are moving from x along the direction y, so along a vector that goes into y, and then you are subtracting the value at x. So you are doing essentially what you do with the ordinary derivative, measuring the function at a point, measuring the function at another point, taking the difference and taking the ratio of the difference in the output to the difference, the variation in the input. The reason for having the norm equal 1 is that instead of, well, if you think of this as a derivative, you should have something like ty in the denominator, and you don't want this. Okay, so that's the reason why you use the normalized vector y. Well, this is something that is defined in multivariable calculus, but of course is essentially a one-dimensional derivative. Once you input x and y, which are vectors, so if you think of real, you have numbers here, numbers here, numbers here, and so the only variable here is t. And so this becomes an ordinary derivative in one variable. And of course, you get a number. Essentially, what you are doing is what you're doing is kind of a thing like this. So say you have a function. This is f of x, say x1, x2. So this is x1, this is x2, and this is f of x1, x2. So this is the case where n equals 2, okay? So f goes from R2 to R. And x is a point in the domain, so could be x is this. And to that x, there corresponds an f of x here. Yeah. So this is f of x. Then you take a vector y, which is kind of thing like this. So this is x plus ty. And this is like considering okay, a point here. This is f of x plus ty. And you are moving along this direction. And so what you get is actually a line which lies on the surface. And you are considering the ratio of the difference between the two values here, which you measure on the z-axis, on the vertical axis, and you take the ratio of this to t. Okay, so you see that actually what you are doing is cutting the surface with a plane that is orthogonal to the x1, x2 plane, a vertical plane, and you are seeing only what happens on that plane. And on that plane, you just see a line, okay? The line for which this is part of the line, okay? So essentially, you are doing a one-dimensional thing. Directional derivatives, as you see, are very important because most of the things in multivariable optimization are actually choosing directions. And so that is an important thing to consider. Being one-dimensional derivatives, all the algebra for the derivatives works for directional derivatives. And so you can do all the rules about, say, derivatives. The derivatives are linear and so on. Some directional derivatives are more important than other directional derivatives, and they are the so-called partial derivatives. So when the derivative, when y equals ei, where ei is a fundamental vector, then the directional derivative f of x ei is called a partial derivative. And as you know, is denoted by this symbol. Sometimes this one. So the partial derivatives are nothing but the directional derivatives where the direction is one of the coordinate axes. And being in Rn, there are n partial derivatives for a function at a point. All the partial derivatives are collected into a vector, which is called the gradient. The vector is a row vector, which collects all the partial derivatives of a function at a point x. Now, there are two numbers here. Two symbols here. One is the symbol for the function, and the other one is the symbol for the point where the derivative is computed. In my notes, I always put the function as an index to this sign, which, by the way, is in LaTeX is \nabla. Because of course it depends on f. You change f, the partial derivatives will change. But of course the partial derivatives usually depend on x, and so on the axis, and so likely the derivatives will change. Now, partial derivatives are derivatives. So essentially, when you compute them at a point, you get numbers. So whenever this vector is computed at a point, you have a function f, you have a point x, you get a row of numbers. Why a row? Well, this will be clear later on. Essentially, this is part of the representation theorem of linear operators. Okay, so what is the problem with partial derivatives? Well, for you, there is almost no problem, because partial derivatives are just derivatives. That they don't tell the whole story about a function. And the reason for this is that essentially what you are seeing, every partial derivative is telling one story, and all the stories together, I mean, cannot possibly make a movie altogether, okay? So you can't join the things together. And you need something more. And the something more you need is actually what is called differentiability of a function. So with all the hypotheses above, well, this is a general case, but Well, I give you the general definition anyway, because this is the one that I have in my notes. So this is definition 111. So we have a set A, which is a subset of Rn. We have a function that maps A into Rm. So the difference in this case is that we are generalizing the thing to a function that outputs not just one number, but m numbers. So essentially, the output is a vector. Takes one vector as an input and outputs a vector with m numbers. We say that a function, well, of course, we have x in A. A is an open set. And we say that if there exists a linear operator which we call df at x from Rn to Rm such that the norm of, I wrote this as a limit, yes. The limit as h approaches 0 of the norm of x plus h minus f of x minus df at x times h over the norm of h is 0. Whenever this is true, we say, so if there exists, then we say f is differentiable at x. Okay. Now, if you remember, well, let's have a look at what is, say, the meaning of this. Well, essentially, this is, again, looks like very close to a derivative. What you're taking is, you're taking the function at the point x, you are moving from x to x plus h, you are considering the difference, and what you expect is something that somehow depends on h, the displacement, okay? And the definition says, well, if you subtract, if there is a linear operator that takes h and outputs something, so the linear operator goes from Rn to Rm. H is in Rn because it's a displacement in the domain. F is in the, so this thing, the whole expression here must be a vector in Rm in the image, because this is in Rm, this is in Rm, this must be in Rm. And if you want to take a vector and in Rn and output something in Rm, you need something that goes from Rn to Rm. The requirement is that this thing must be linear. Now, if there is a linear operator such that this, the norm of this, of course, you can't take the numbers because there are no numbers. This is a vector. Over the norm of the displacement is 0, then you call this function differentiable. Essentially, what you are saying is that the change in the output can be measured by something that is linear, okay, in the displacement, in h, in the variation in the input. Now, if you compare this to what you said last year, so if you remember the definition of the derivative in one variable is this one, is the limit as h approaches 0 of f of x plus h minus f of x over h. This is the definition of the derivative at x. Can you see this? Yes. From this, you can multiply by this by h, and you get that f of x plus h minus f of x minus h f prime of x, because you can do so, is something that is approaching 0. Okay? Well, let's say, yes, is approaching 0. So is little o of 1. Sorry, didn't say it. I shouldn't have written this way. Should have written the other way. This means that f of x plus h minus f of x over h minus f prime of x is little o of 1, which means approaching 0. If you multiply this by h, you get f of x plus h minus f of x minus h f prime of x equals little o of h. So this is exactly the same thing written in one variable calculus. Okay, exactly the same as this one. Actually, they are the same. If m equals 1 and n equals 1, the two things are exactly the same thing. What you see what you have here. What we are saying is that this is the ratio, the difference quotient of say f and h, and so this is the slope of the line joining x f of x, x plus h, f of x plus h. Okay, and as h approaches 0, this number approaches the derivative at the point. Okay, which means what? Which means that if you subtract the tangent line, which is this one, what you get is something that is negligible with respect to h, because you have removed the linear part. Okay, you have removed the first degree approximation of the function. It's like taking a function, considering the tangent line, and then considering a function which is the function minus the tangent line. Of course, at that point, you get something that goes to 0 and is not linear. Well, it's not linear in terms of h, because the linear part is approximated by the tangent line. Any question about this? No? You see, what you have here is exactly the same thing, exactly the same. The problem is, when you define the differential in one variable, you don't see, because this is a number. And in the general case, the f prime is actually this, df. Why is that? What is the differential here? The differential is actually a linear operator, but the derivative is a linear operator. Actually, it's not presented as a linear operator because it is a number. And of course, I mean, people say, why should I worry about linear operators when I have numbers, which are basic things that I know? But actually, the derivative is a linear operator. The fact is that you are mapping R into R, so n and m equals, both of them equal 1. And so you don't see, because everything collapses into just one thing, which is a number. In this case, this is not anymore true. You need a linear operator that maps h, which is a vector in Rn, to something which is in Rm. And of course, the linear operator is something that maps Rn into Rm. So that's the definition of differentiability. And the definition is the one that is actually that is important. So in one variable, you don't see that. When you have one variable functions, you don't see the difference because you just see numbers. In multivariable functions, you see the difference because this is the important thing. And whenever this is true, the function is continuous, all the partial derivatives exist, many good things. The partial derivatives themselves in this setting are not enough to guarantee a number of things. But luckily for you, most of the functions that are used in machine learning and applications are actually essentially polynomials or something like that. So in most of the cases, this is not a problem, okay? So you have functions are differentiable, and so you can compute everything. Now, a word about the size of this. Yeah. Yeah. What is the meaning of nonlinear with respect to h? Well, exactly this. This difference is something that goes to 0, of course, because this goes to 0 as h approaches 0. Yes, and this goes to 0 as well. What you know from the definition is that if the function is differentiable, the difference here goes to 0 much faster than h. Okay, so you have removed what you have. The derivative proves that there is a tangent line essentially. Okay, that is the geometrical view of the same thing. If there is no tangent line, you cannot have a derivative because you cannot. This thing is not true anymore. That is the point. So in the general case, we have f of x plus h minus f of x. Let me just write the differential as a matrix, because essentially it is a matrix. By the representation theorem, I'm using a thing that I explained in the other course now. The representation theorem tells you that every linear operator that maps Rn into Rm is represented by a matrix, okay? So what is the matrix? Well, we don't know, we'll see in a moment. But we have a matrix times H, okay? So this is what previously was called the f of x. And of course, again, in the one-dimensional case, this is a matrix, a one-by-one matrix, but a one-by-one matrix is just a number. Now, in the general case, this is a vector. Think of the case m equals 1. So you have f from Rn into R, which means what? F of x plus h minus f of x. Oh, this is a number. This is a number. You need a number here. Otherwise, you can't get, you can't perform the operation. But this is a vector, so this is h1, hn. What do you need? What is the matrix representing? What size is the matrix A? Well, you need a matrix that maps Rn into R. If you look at the representation theorem, matrix A has as many rows as the output and as many columns as the input. So matrix A must be something like this, A1, AN. Otherwise, you don't get a number. It's kind of mechanical reason. But of course, it's written in the representation theorem. And so you see that the differential in the scalar, when you have f of from Rn to R, must be a row vector, because it's a linear operator that maps Rn into R. Good news, this linear operator is actually the gradient of f. Which in a sense extends what we know in one dimensions to many dimensions. We just, instead of writing one derivative, we write n derivatives. So that's the reason why I define, I stress the fact that the gradient is a row, because you see it as a linear operator. Let me tell you that in many cases, we will exchange rows and columns because in finite dimensional spaces, actually, you can always, of course, consider a row vector as a column vector. It's just a matter of looking at things in a slightly different way. In some books, the gradient is considered a column, so they need a transpose to make things work. I didn't use this, but of course, I'm telling you this because you may read some books about these topics, and maybe, of course, the conventions are different. Okay. What happens? Any question about this? So what happens when actually F maps Rn into Rm, and m is greater than 1? Well, in that case, f of x plus h minus f of x, this is a vector in Rm. This is a vector in Rm, and you need a times h, you need a vector in Rm, but then you have a vector h1, hn, and of course the matrix must be an m by n matrix. So m rows and n columns, because otherwise you can't make the product between the two. What are the numbers here? So this is the matrix A. The good news is that A is actually a column of gradients. Essentially, every row is the gradient of the components of F. Since F is mapping Rn into Rm, there are m outputs. It's like having m distinct functions, okay? Real valued functions. You take the first, you compute the gradient. This is the first line in the row, in the matrix A. Then you take the second function, you compute the gradient, you get a row, and this is the second row in the matrix, and so on until you get to the last one. This matrix, a matrix which is computed using the gradients, is called the Jacobian. I'm just mentioning this because this is part of the, say, setting, but actually we will be using mostly the gradient. And something so we are ending at 10 to 1. Okay, I know. We'll have a break at some point, okay? Okay, so this is the complexity that is, unfortunately, that is required if you want to move from one variable calculus to multivariable calculus. Instead of having one derivative, you have many derivatives. And of course, the situation gets even more complex if you have more than one output. There are a few things I want to say before the break, and this is definition 114. Assuming f is differentiable at x0, then in this case, we have the partial derivatives. So the theorem tells you whenever f is differentiable, you have all the partial derivatives, you have the gradient, everything works in the way that is expected to work. And what you have is that a function t of x, which is defined as f of x0 plus the gradient of f at x0 times x minus x0, this function is called the tangent plane. To f at x0. If you remove the vector signs here, and if you change the gradient to the derivative, this is actually the equation of the tangent line in one variable. So again, the meaning is the same. And in general, of course, you have more than one variable. So when n equals 2, you have a tangent plane, a real plane in 2 dimensions that touches the surface at possibly one point. And if n is greater than 1, you have what is called an hyperplane, but essentially a linear equation in n variables. Okay, which means an n minus 1 dimensional space. Another thing that I don't know if this will be used somewhere. Anyway, then we have theorem 115, which is the chain rule. And the chain rule says essentially that you have a function f that goes from Rn to R, which letter do they use? Rm. And a function g that goes from Rm into Rp. And you assume that f is differentiable at x, and g is differentiable at f of x. What happens is that if h of x is defined as g of f of x, so you take the composition of f and g, the differential of h at x equals the differential of g at f of x times the differential of f at x. So this is exactly, if you write it this way, is exactly the same as the chain rule in one dimension. The derivative of the composite function is what? It's the derivative of the outer function when you consider the inner function as the input. So the derivative of g with respect to f of x, considering f of x as another variable, and then you multiply by the derivative of the inner function. What is interesting is that formally this is exactly the same in multivariable calculus. Of course, in multivariable calculus, these are not numbers. These are all linear operators. And this is a matrix, this is another matrix, and this is another matrix. And the rule for the matrices work in this case because, well, if you look at the derivative of the differential of h must be, h is mapping Rn into Rp, so it's a P by N, and this is a P by M, and this is an M by N. Okay, so the matrix product rules apply here and work perfectly. One final thing, which is very important for us, because we will be using this a lot, is what happens with second derivatives. So say you have a function. So this is the function, f of x, one variable function. The function is smooth, so it's differentiable. We have x here, and we have f of x here. This is the ordinary mapping, x, f of x. But we know that we can build another mapping, which is x, f prime of x. At every point, we associate not the value of the function at x, but the value of the derivative, that is the slope of the tangent line, okay? This is a mapping, the mapping that goes this way, and this mapping is called the derivative. When you say briefly that if f of x equals x squared, the derivative of f of x is 2x. Now, this is another function which associates to every point in the domain, not the point in the image of x, but the slope of the tangent, well, the derivative at x. And this is another mapping. This mapping is called the derivative and takes a point and associates what? Well, in the one variable case, again, this is a number, so you don't see the difference. But actually, that number now we have seen is not actually a number, is a linear operator from R to R. In the general case, think of a function, as I did before. So say you have a three-dimensional setting, and you have the function like this, and you have x, and you are here. And of course, above x, there is a tangent plane, okay? So a plane that touches the surface at this point. If you move from x to another point, say here, sorry, this is, okay? And you move to another point here, then of course the tangent plane has changed. Well, you see something geometrical here, something real, which is the plane, but actually what you should see is a linear operator, which takes the form of a plane because it is a gradient, actually. And now the question is this mapping differentiable? Because it is a mapping. What is this mapping doing? This mapping is taking a point in the domain, Rn, and associating a linear operator there. So if you think of the two-dimensional case, which is, well, the n-dimensional case, what you are doing is taking x, a vector, and instead of associating f of x, you are associating the gradient of f at x. You see that you are doing the same thing. So every vector, you take a vector in the domain, you associate another vector in the image, not a point, the vector. Of course, this is a mapping. Is it differentiable? We don't know. Well, for the cases we will see it is differentiable, actually infinitely many times. With polynomials, this is always true. What is the differential of this? Well, the differential is something that must map x to another vector, the difference between two gradients, okay? Because this is what you do when you do a mapping of a differential. What is something that maps Rn, a vector in Rn, into another vector in Rn? What is the object? Sorry? A square matrix of order n, because by the representation theorem must have the same sizes in both, the same number of rows and columns, both equal to n, because you are mapping an n-dimensional vector into an n-dimensional vector. So the second differential, which is usually represented by this, is actually associated with a matrix, which is called the Hessian matrix. And no surprise that this matrix, being the matrix of the differential of the gradient, is built with the second derivatives, okay? So this is the reason why there is a Hessian matrix, not just So the action matrix, f, h, f of x, is actually a matrix where you have the second partial derivative of f with respect to x 2 times, then, x1 2 times, then the second partial derivative of f with respect to x1, x2, up to the partial derivative of f with respect to x1, xn. And the same here, and then the final row is the second partial derivative of f with respect to x1, xn. And here the second partial derivative with respect to xn 2 times. Sorry? Yeah, yes. Well, formally, yes. Technically, no. Because, yes, should be in theory, they should be different, but unless you choose very special cases, they are equal. So this matrix is symmetric, okay? So the numbers here and the numbers here are equal. It's not that easy to find a matrix for which the Hessian is not. There is a theorem, which is called the Schwarz theorem, that says that if the partial derivatives exist and they are continuous, then this cannot happen. So you need very strange cases, which, I mean, they do exist in multivariable calculus, but they are kind of pathologic. So we are not considering them, okay? So essentially, the matrix is made up with all the second derivatives, partial second derivatives. Along the diagonal, you have the second derivatives taken with the same variable twice. And the remaining derivative, the first one is the second derivatives with respect to x1 and with respect to all the other variables, the same for the second and the last row. And as I said, this matrix is symmetric. Again, this is a matter of notation. I've used H. Some books use this symbol. I don't like it because, well, in physics, this has a different meaning. So I always used H in my notes. But if you read some books, some books are using this symbol as for the Hessian matrix. So essentially, and now I think we can make a break now. So essentially, what we have done is viewing all the things that we have done last year in one variable calculus and partly in multivariable calculus, reviewing them and explaining them, say, in this new setting. We missed one important thing, but this is so important that I want to move it to the second part of this lecture. So is 11:30 right now, so 15 minutes approximately, we'll be back, okay? Okay, guys, can you hear me, you guys online? Yeah, okay. Okay. Okay, so I am now presenting the last topics in this review of, say, differential calculus. And the last part is about, say, few things that are actually useful, and we yes, we will see back in many proofs of the, say, numerical part. Okay, so page 5, page 4, yes. Okay, so now I'm going to tell you, well, this is theorem 119, which is Taylor's theorem. Taylor's theorem is very important in mathematical analysis. Probably is one of the most important theorems in analysis, in mathematical analysis, because it gives you an approximation of a function in terms of the derivatives of that function at a point. The assumption is that the function is differentiable, and whenever the function is differentiable as, say, a number of times, we can write an approximation of that function that uses, as I said, the derivatives. The approximation is a polynomial. This is the important fact. So I will start giving you the versions, the one-dimensional versions of this, for two reasons. First of all, because we compare the two versions, the one-dimensional and the multi-dimensional version. And second, because actually we will be using the one-dimensional version in some applications. Okay, so let's see. So we have this is the one-dimensional case. So it uses f, say, from A subset of R to R. We assume that f is continuously differentiable, which means that it's not just differentiable, but the derivative, in this case, the differential, is continuous. As I said, this is something that usually people in the machine learning group don't worry about. I mean, they consider everything. Let's say that every group that uses mathematics considers all the hypotheses true, always. So economists say whatever the function, they have, it's always a function that has infinitely many derivatives and things like that. Only mathematicians are worried about these things. Okay, so if f is continuously differentiable, then for every x in A, for every x0 in A, we have f of x0 plus h equals f of x0 plus f prime at x0 times x minus x0, no, h, I used h, times h plus little o of h. Little o means that this is, just as a reminder, little o of h means this quantity over h goes to 0 as h approaches 0. Of course, this is true as h approaches 0. This is one-dimensional version with just the first derivative. So essentially, this is saying nothing more than the definition of the derivative. It says, if you take a function at the point x, 0, and you move slightly from that point, then the value is actually very close to the value of the function at x0 plus the displacement times the derivative. So essentially, you are moving along a straight line, and the straight line is the tangent line. That is what you're saying. Essentially, approximately, and all these things are actually written here. Okay, this term tells you that that there is an error. You're not exactly in general on the straight line, on the tangent line. So the line is not the tangent line, it's curved line. But if you stay sufficiently close, then this is negligible with respect to h, which has that meaning. Okay, and this is the one-dimensional meaning. There is another version of this, which sometimes we will use, which is this: f of x0 plus h equals f of x0 plus f prime at x0 plus theta. Did I use theta? No, t. th times h, where t is a number in 0, 1. The second version, sorry, put it here. The second version of the same theorem, well, the theorem is essentially the same. We will see this also in say, with the second derivative. Well, there is an uncertainty here. The uncertainty is written here because we don't know. This is not a function. You remember from last year, this is a class of functions. All the functions such that divided by h, the limit is 0 as h approaches 0. So you're not saying what this is. You are just saying there is a function that does this job. There is another way to say to pack the uncertainty. So the meaning is the same. The packaging is different, and the packaging, the uncertainty now is not in this term, is in this number t, which says, well, you can get the equality, and this is an equality, but the price you pay is that you don't have to compute the derivative at x0, which is something you are supposed to know, but you have to compute the derivative at the point which is x0 plus th, which means, and t is a number between 0 and 1, which means that this number is in between x0 and x0 plus h. So it's a number between x0 and x0 plus h. And it doesn't tell you where. So still, there is an uncertainty. The only difference is that here the uncertainty is not controlled by the derivative. Here it is. If you look closely, this is actually the statement of the mean value theorem, which says there is a point in the interval a, b such that the derivative at that point equals f of b minus f of a over b minus a. Is exactly the same thing. So this is actually an instance of the mean value theorem. Okay. This is not the only way to write these things. There are many ways in which you can write something, and the last term you write can be written in this way or in this way, or there are many ways to write these things. Okay. This is for the first derivative. Then we have the version with the second derivative, which is more or less the same, again in the one-dimensional case. So it is still in theorem 119. Maybe I can write it here. Maybe. If I remove this, put this here. If f is twice differentiable, which means you have also the second derivative, then you can write the same thing in more, say, in a longer way. F of x0 plus f prime at x0 times h plus 1/2 second derivative at x0 plus times h squared plus little o of h squared. And again, in the other version, f of x0 plus h equals f of x0 plus f prime at x0 times h plus 1/2 second derivative at x0 plus th times h squared. Again with t in 0, 1. If you can pay more, which means the function is even twice differentiable, there is the second derivative, then you can say more. Because in this case, in both cases, well, let's say, in the first case, this is quite obvious. The function at the displace point equals the same thing, but then we add another term, which is of the order of magnitude of h squared. H is supposed to be small. And it has the second derivative. And then what's left is something that is negligible with respect to h squared. This now is becoming important. These numbers are important now because what we are going to do from next Thursday on is to explain how to compute these things. So this is mathematics, and we say as h approaches 0 and things like that. When we be moving to, say, computational, to numerical things, then h will be a number which can be represented in the machine, so it's something that the machine can understand, but it's not 0, and it never approaches anything. I mean, it's just a single number. It could be 10 to the, I don't know, -5, -6, or something like that. And of course, being negligible with respect to the square of this number could be something very meaningful, because it says, well, it's probably something that you cannot even see in the application. Oh, that is very unlikely. Again, the same trick as before works here. Instead of, say, enclosing the uncertainty in this little o term, you can put the uncertainty in the second derivative, in the point where you compute the second derivative. And you can do so actually for every. Taylor's theorem doesn't say anything about the number of derivatives. If the function is differentiable n times, you can do this for n derivatives and then stop at some point, okay? Now, what is the important thing here? Well, the important thing is that if you consider h as the variable, which is something you typically do, because you know in numerical problems, you start with some data at some point, and you want to move from that data to another point. So x0 is supposedly given, and you want to move from x0 to x0 plus h. And the h is something which is, in theory, say, small. But in terms of h, this is actually a linear function. This is a number. This is a number. This is a function. This is a quadratic function, is a second degree polynomial, so it's a parabola in terms of h. Of course, if you discard this, or if you consider this, okay, this is more clear from the second form. And the idea that we will see is that sometimes this can be controlled in some way. And so, of course, we know that whatever the formula we will be using, we will not get the exact value, but this is something that you take, for granted when you are solving approximately problems, okay? And the idea is that whenever we have a function, unless the function is quadratic, which is something that sometimes happens, the idea is that instead of using the function, we will be using the Taylor approximation. And with the Taylor approximation, actually, we transform the function into either a straight line or a parabola, and then this becomes easier to manage. So there is a good reason, say, for learning so many things about parabolas in high school. Okay, now we turn to the multidimensional version of this. Well, the first part is actually more or less the same, because in the multidimensional case, which is theorem 120, in the multidimensional case, A is a subset over N. Again, all the things, if F is continuously differentiable, if F is continuous, so F goes from A, which is a subset over N, to R. X0 is a point in Rn in A. If F is continuously differentiable, which means the function is differentiable and the gradient so exists at every point, then we can write f of x0 plus h as f of x0 plus the gradient of f at x0. I left the f above and not in the index, times h plus little o of the norm of h. And this is one version, and the other version is that f of x0 plus the gradient of f at x0 plus dh times h. You see that apart from few details, the vector sign, the norm in the little o, well, this is exactly the same formula as before. And again, this is not a polynomial. This is a 1 degree. Anyway, this is a linear function in H. And if f is twice differentiable, then we can say f of x0 plus h equals f of x0 plus the gradient of f at x0 times h plus 1/2 h transpose the Hessian of f at x0 times h plus little o of norm of h squared. And again, the other statement is the same, but h transpose Hessian of f at x0 plus th h. Of course, in both cases, t is a number in 0, 1. Yeah. Yeah, this is an n by n matrix. No, it's still a matrix. This is an n times 1. Sorry, this is H transpose. So it's a 1 times n times n times n times n times 1. it represents the contribution. It's actually this, the same as this. The function goes from an Rn to R. So all the values here are numbers. So you see, this is a number. This is a function that, say, given an input, x0 produces an output, which is a number. A vector as an input, a number as an output. So Rn to R. So this is a number. You move from x0 by an amount h, and you get a different number. Now the theorem, Taylor's theorem tells you that number is approximately the value at the point x0 plus the gradient times the displacement. And this is a row times a column, so it works. It is a number. And then you need this special form, which is, well, you know, a quadratic form, because we have seen this last year. This is actually a matrix, H, and a row vector and a column vector here. You need this special arrangement because you want to get a number. Actually, there are good reasons for this, because this is a mapping, and you multiply this by this, you get a column vector, and this is a row vector, so you are taking an inner product of the two things. Essentially, you want something which is quadratic in the h's, in the components of h. And to get something quadratic, you need this form. You need the quadratic form. The idea is exactly the same as the idea that we introduced last year. If you want to write something which is depending on the squares or the second degree function, the best way to write this is to use because you have to allow for all the possible products, okay? So you have x1 times x1, which is x1 squared, x2 times x1, x1 times x2, well, they are equal, and so the matrix must be symmetric. But apart from that, you need both products, and so you need both H transpose and H, because you need to get all the things. And essentially, H, say, produces this product, the one on the left, on the right, produces a column vector which contains all the components of H, and then you multiply by the other one. Is a way of rearranging the function. Yes, please. With this, well, it's very complex, because you have to distinguish among all the cases. You have the third derivatives here, and of course it becomes, you have three ways of defining, of computing a derivative. Yeah, but we're not considering this because of well, essentially the formula works for every case. In applications, of course, you usually stop here. The reason for this is that last year you learned that this is actually the key to proving some theorems about finding minimizer and maximizers of functions based on the properties of H, and we will still make use of these properties now in a slightly different way, because we are not considering now, since what we are going from a theoretical point of view, you keep these things because you know they are there and you cannot neglect them. But from a numerical point of view, you just discard them, and so you are left with parabolas, straight lines, things very easy to manage. Okay. I have written an example in my notes, which is example 121. Just example 121, you have a function f from R2 to R. The function is defined in f of x x1, x2, I used x and y. Sorry, well, it's okay. xy equals e to the power of x squared plus y. Of course, this is an exponential, so this differentiable as many times as you want. And so we can compute the gradient and the Asian matrix, okay? So the gradient of f at the point xy is the partial derivative of f with respect to x and the partial derivative of f with respect to y. The partial derivative of f with respect to x is what? Is e x squared plus y times 2x. And the partial derivative of f with respect to y is e x squared plus y times the partial derivative with respect to y, which is 1. Well, I write it this way. So this is e power x squared plus y times 2x1. Yeah. Factoring out the common exponential. For the Asian matrix, well, the Asian matrix is the second partial derivative of f with respect to x squared, second partial derivative of f with respect to x with respect to y, second partial derivative of f with respect to y with respect to x, and second partial derivative of f with respect to y 2 times. So we take the components of the gradient and we compute the partial derivatives of each component with respect to the two variables. So the partial derivative of this with respect to x is, well, derivative of the first, which is e x squared plus y times 2x, times the second, which is 2x, plus the first times the derivative of the second. The partial derivative of the first with respect to y, well, x is now a number, so is e to the power of x squared plus y times 2x. The partial derivative of the second of the partial derivative with respect to y is, well, exactly as before, is e x squared plus y times 2x. And the second partial derivative with respect to y 2 times is e x squared plus y. So we can factor out this and get 4x squared plus 2, 2x, 1. Yeah. So now for this function, the gradient and the Asian are defined everywhere. So we can write the Taylor expansion. We need a point, a starting point. And in the example, the starting point is 0, 0. Okay, so we are considering 0, 0 as x0. Well, it should be a column, actually. So, and we want to find what is f of 0 plus h. sorry, I should write as a column here. This is 0, 0, and H is H1, H2. Okay? So, well, the formula says that f of 0 plus h equals f at 0 plus the gradient of f at 0 times h plus 1/2 h transpose the Hessian of f at 0 times h plus little o of the norm of h squared. So this is telling us that f of h is f of 0. Now f is e to the power of x squared plus y. X squared is 0, y is 0, e to the 0 is 1. So this is 1 plus the gradient. The gradient is this. This is 1 at 0, 0. This is 1, and this is 0, 1. So the gradient is 0, 1. Times h1, h2 plus 1/2 h1, h2 times the Hessian matrix. The Hessian matrix is this one. The factor in front is e to the power of 0, which is 1. Here you have 4 times 0, which is 0 and 2. So you have 2, 0, 0, 1. So this is 2, 0, 0, 1 times h1, h2. Which means 1 plus h2 plus 1/2 h1, h2. We have to multiply this. First row, only column is 2h1. Second row, only column is h2. And this is 1 plus h2 plus 1/2. This is 2h1 squared plus h2 squared plus little o. So in the end, this is 1 plus h2 plus h1 squared plus 1/2 h2 squared plus little o. Well, that's the thing. You could get here, say, very quickly, if you remember the say the Taylor expansion of ex squared and e to the power of y. Well, of course, this is for the this is just an example of the thing, but the idea is that x squared plus y equals e to the x squared times e to the y. And this is 1 plus x squared plus something, and e to the y is 1 plus y plus something. And if you multiply these things, you get exactly the same thing. Around 0, of course. But this is not. This is just a trick, and works just because the starting point was 0, 0. Okay? Any question? This was just an example to see how things work. And you get numbers, because of course h1, h2 are numbers, so you see from this that as you move from 0, 0, these are second degree terms. So if h1, h2 are both small, these are much smaller than this. So essentially, this is the big part, the first degree part, and the second degree part is like this. Okay. Another definition, another thing that I think I told you this thing last year. I mean, this is definition 122. So if you have a function f from Rn to R, then the level set of f at level C is the set the x's in Rn such that f of x equals C. So the level set, I mean, is, well, it's just defined through an equation. So the set of all the values that for which the function takes a given value C. In the two-dimensional case, when I say two-dimensional, I mean the functions from R2 to R. Of course, we can visualize these level sets because they correspond, they correspond to, say, to what we get if we cut the surface at a level C. Okay, so if you cut this surface with a plane at a level C, what you probably get in this case is something like, I don't know, something like this, okay, which sort of, no, it's bad. Okay, so the idea is that you are cutting a plane and you are looking for all the x's such that f of x equals C. So this is the plane at level C that cuts this curved surface, an horizontal plane. And actually the level set is the set of points on the domain, the x's in Rn, such that this is true. These are very easy to get if you use some software like, I don't know, Desmos, GeoGebra, Wolfram Alpha, because you ask for the level set. Or you just write the equation like f of x equals C, and then they plot, because this is actually an equation. And so what the software does in this case is solving the equation, not thinking of the section that you get if you cut something. I mean, it's like solving the equation. So they have some tricks to solve equations, and they plot the solutions of the equations. Okay, so some obvious cases, like, say, for example, if f of xy equals x squared plus y squared, or say x1 squared x2 squared, well, the function here is like this, is actually kind of a thing like this. And if you cut it with horizontal planes, what you get is you get circles. And this is obvious from the algebra, because if you set x1 squared plus x2 squared equals something, if that something is non-negative, you get a circle. And the equation of the circle is this one. In this case, the level set exists for all the non-negative values. For the positive values, you get actual circles. For C equals 0, you get just a point. And for the negative axis, you don't get, the level set is empty. You might think of this as the preimage of the function f. foresee. Why am I mentioning these things? Because of course these things are useful only if you can see them, and you can see them only if you have functions of 2 variables, or maybe 3 variables when you write an equation with 3 variables in space. So any surface could be seen as the level set of of some function for which this surface equals something. Why? Because some of the examples, the critical examples, can be easily seen with level sets. There is one example that I want to mention for which I also produced this. Of course, this is not something in LaTeX. This is GeoGebra, I guess. Think so, or maybe, I don't know. And the function in example 123 So I'm just mentioning this because, yeah, it is important. Example 123 is the so-called Rosenbrock function. And you might think this is a complex thing. It is not. F of x1, x2, so f goes from R2 to R. And f of x equals 100 times x2 minus x1 squared, everything squared, plus 1 minus x1 squared. Just a polynomial, a 4th-degree polynomial. And, well, actually, the definition of the Rosenbrock function as, well, this is just the case with the 100, but could be any number. I think you control this number and this number. I'm not sure about that. Why is this function? Why am I mentioning this function for this? Well, the level sets of this function are plotted in figure 1.1. And as you see, the level sets are somehow, I'm kind of copying my say the drawing is like this and this. And then at some point you get something which is like this. And you get actually curves like this in this case. Then you get something like this, okay? So again, the purpose here is to find the minimum. Again, this is a sum of positive power of squares. So the minimum is when, if there is any, where the two, say, numbers here and here are 0. For this is quite easy to get, because you get, if x1 equals 1, that you get 0, which is the minimum value you can get out of this. And when x1 is 0, if x2 is 0 as well, when x1 is 1 and x2 is 1 as well, you get 0 also in the first term, okay? So 1, 1 is a minimum for this function. And it is a global minimum. And 1, 1 is here. The sketch of the level sets tell you that if you reduce the level, so as C decreases, you get closer and closer to this point. But the point is that when you are here, you don't see this this minimum, this minimizer here. You don't see it because the level set is not like this that goes everywhere. I mean, it stops here. So this is the reason why this is called the banana function, because there are these shapes look like bananas. That is the idea. The fact is, it's quite difficult to approach this point Because what you see is that if you can picture out this thing, say, three-dimensionally, you see that actually these are the same level, and then suddenly something goes down in this region, very down, up to get to 0 in this region. So this is what is called a very narrow valley, in which it's quite difficult to enter, in a sense. You don't see the valley if you are outside. That's the point. But at some point, of course, you start seeing the valley. Of course, if you're very close to. But the idea is that when you are solving a problem numerically, you are not that necessarily that close to the solution of the point. Sometimes you don't even know where the solution is. And the solution is not far from, say, a starting point like 0, 0, 1, 0, or something like that. So this is the problem. That function was invented by this guy, Rosenbrock, in an article. I think you can find the article online somewhere in 1960s or something. So it's not that, of course, it's designed on purpose to make things very complex, to algorithms, to make algorithms' life very complex. That is the idea, okay? And this is used by many softwares to test their, say, ability to solve problems. Okay, we are left with a couple of things. And the couple of things we want to say are actually two properties, fundamental properties of the gradient. I already mentioned these properties last year. So I'm quickly giving you the statements. I also included the proofs here, but of course, I mean, it's just for you, I mean, for the, say, the guys interested in the mathematics behind this. I know that you are all interested, but so the first one is theorem 124. So we have a function f from Rn to R, which is continuously differentiable. Then the gradient of f at x0 is orthogonal to the tangent vector to an arbitrary smooth curve passing through x0 and determined by f of x equals f of x0. So essentially the level set at x0. Usually people don't state this theorem in this way, but they say, just briefly say, the gradient is orthogonal to the level sets, which is the quick translation of the shortcut to this. The idea is this one. You have a function, say, I take again the example with the, so f of x1, x2, x1 squared plus x2 squared. So you take x0 on say somewhere here, and you have f of x0. So this is x0. And then you have the level set. The level set is that curve, is a circle at this point, okay? So actually the level set stays down in the domain, so it's here. Okay. The level set is this one, is the projection of the circle you see cutting the surface on the domain. Well, the theorem is telling that if you take the level set and when you say a smooth curve means that, well, the level set is usually smooth. I mean, the function is not. And you take this, the tangent line, and you take the gradient. Actually, the gradient, well, in this case, the gradient will point this way. The gradient and the tangent line at this point are orthogonal to one another, which means that if you want to move along the gradient, you have to choose the direction that is orthogonal to the level curve. This is related to the next theorem, but this is a property. This property is quite easy to prove. It's just a matter of manipulating the thing and using the chain rule. Okay, so you can look at the properties. Not, I mean, it's not that important to learn the proof, but it's an interesting application of the chain rule. Essentially, what you are doing is that if you move along think of what is the level set? The level set joins all the points for which the value of the function is the same. Now think you are moving, you are walking along this circle in the surface. You constantly see, you are constantly at the same level. So if you consider the gradient of the function, what is the gradient measuring? The gradient is measuring the variation in the function. But if you are moving along this circle, the variation of the function is 0, because you are at the same level. Okay? So, and by the chain rule, this is actually, the derivative of the function is actually the gradient of the function times the tangent line, and this gets the property. So that is the idea. So gradient orthogonal to the level sets, and second property, which is theorem, I don't know, which is theorem, where is it? At the end of page 24, 25. What is 26? Yeah, got it. Okay, theorem 126, which says the direction of maximum rate of increase of function f from Rn to R at a point x0 is orthogonal. No. Where is it? Oh, yes. Stupid. Is orthogonal to the level set. At x0. So, The maximum rate of increase is that one. So if you move from a point, and of course you are looking, there are infinitely many directions at that point. If you move along the level set, there is no increase and no decrease at all. So there are other directions. And the theorem is telling you, if you want the maximum rate of increase, go perpendicular to the level set, which is exactly the direction of the gradient at the point, okay? So this is another way to say that the gradient is the direction of maximal increase in the function, rate of increase in the function, okay? Actually, say we will be interested in not in the rate of increase, but in the rate of decrease of the function, because usually we look for minimums of minimizers for the function. So we will be looking for not the direction of the gradient, but the direction opposite to that of the gradient, that is negative the gradient. The two theorems together give us a method which is called, and this is part of the thing that we see next Thursday, the theorem of the idea of gradient descent. You start at the point, you measure the gradient tells you where to go to increase the function, you want to decrease the function to get to the minimum, you follow the other direction, the opposite direction of the gradient. And then you get to a number and another point, and then you repeat the process again and again and again. Computers are very good at this, and so they do this thing over and over and over until at some point you get, hopefully, to the minimizer of the function. That is the idea. This is based on these two things. The idea of being orthogonal is very important. We will be using this in an example, which makes very clear that some say the idea of this one, which is called the gradient descent, is a good idea, but not probably the best thing to do in some cases. Okay. There are also a couple of examples here at the end. One of them is taken from last year's notes, so is just a copy and paste from last year's notes. And next Thursday, and for the next two Thursday, we will talk about what is chapter 2 in these very short notes. So we will start from looking at first one-dimensional optimization, so along a direction, then we will move to multidimensional optimization. See you on Tuesday for the other course. Okay, thank you guys.